welcome everybody to our first meeting of 2021. Thank you for coming. I'm really pleased to see such a big turnout so soon after the new year. I guess people are eager to get back to work. We have our usual format of two very brief 15-minute teaser talks. One by Paul Macklin from Indiana University on collaborative modeling work that he's been doing on in-host viral replication and immune response. And then another talk also on a similar subject using different methodologies by Bard Ermentrout from Pitt. We're also going to have Reinhardt talk a little bit about the steering group meeting that's going to happen tomorrow. And if we have time, I would like to have some discussion about subgroup updates. And finally, I would also really appreciate people's suggestions for future speakers. As a reminder, this meeting is being live streamed. It will be recorded and made available. So I need to let you know that. A reminder who we are. I'm James Glazier, Indiana University, co-lead of the working group with Reinhard Lavenbacher, University of Florida. Web administration by Jim Sluka, and you've had probably emails from Bruce Shapiro, who has been kindly helping organize. You may also have had some emails from John Rice, who's also been helping organize. We do have a Slack channel. So far, it hasn't been widely used, but we would encourage people to use that. And if you need access to it, please ask us and we will provide it. There's also the IMAG MSM wiki page. People who have signed up for the working group are welcome to edit, put material there, and make suggestions. And so we would, again, if you have any technical issues, please contact us with that. Without further ado, then, I would, John, are you asking for, is that a hand up there, or are you asking, you want to say something? No. Okay, I thought I had a request for a comment. So without further ado, our first 15-minute talk will be from Paul Macklin, and I will turn the screen share over to you, Paul, and look forward to having your presentation. Appreciate you being willing to talk to us.
Well, thanks very much, James, for inviting me here today to talk with the group, and wonderful to see a lot of familiar faces and a few new faces here as well. Hopefully this is sharing my presentation, and I'm going to just change it to make sure that you have the full screen view of it. So kind of we have more slides than we should have time for. I didn't realize it was 15 minutes instead of 30 minutes until just I read your email about 2 minutes ago, James. So we will give the super abridged version of these slides here today, but very happy to answer any questions afterwards, one-on-one or in the Slack channel for the group, and particularly be a great place to take the discussion. The work that I'm pointing out here today really is a team effort. There's absolutely no way we could do this by ourselves, and so I want to just thank at the very beginning our wonderful coalition of modelers, immunologists, virologists, and others across the US, Europe, and other places, led in particular by my postdoc, Michael Getz, and PhD student Yafei Wang, who I'd like to put a little plug in, who will probably be finishing his PhD this summer and looking for a postdoc position, and he's fantastic. So thanks for our coalition for contributing to this, and also thanks to sponsors who have helped with this work. Both, recently the Jane Koskinas to Juvenis Foundation for Health and Policy that gave us kind of an emergency Kickstarter grant, and then more broadly for methodologic funding from the Breast Cancer Research Foundation, the NCI, and the NSF. And so, as we all know, COVID is a multi-scale problem and involves processes going all the way from the subcellular scale all the way to the tissue scale and the system scale, linking processes like virus moving in the extracellular spaces, binding to a receptor, in this case ACE2 receptor, being endocytosed or brought into the cell, releasing and encoding and releasing the virus and releasing its RNA contents, which then eventually is going to start pumping out viral proteins. Those get assembled back. And then get assembled into new virus particles, and then exocytosed back out of the cell and spread in the extracellular spaces and go on to infect other cells. But then, of course, you have a whole bunch of other processes going on. Some of the more important ones we have to bring up here to set up today's talk is that when a cell is infected, it can detect that actually. It has its own antivirus responses, in particular interferon signaling, where the cell will start pumping out interferons, both internally to help reduce cell virus replication, and also send that out extracellular as a kind of like an early warning that something's going on here, and cells nearby will then respond to that interferon resignaling by also reducing the viral replication. And then there's a paracrine signaling response where actually a cell receiving an interferon response will send out its own interferon signal to help further spread the word that there's an infection nearby. And of course, then all the other immune processes that you're probably very familiar with, like macrophages scouring the tissue looking for dead material, and they can become activated. Dendritic cells, again, kind of scouting out the tissue, looking for signs of infection, and then sampling those, and then bringing back what they've learned, leaving the local tissue and going to the system scale, going to the lymph node, where they're going to present what they found, present the antigens, and help ramp up a more specific T cell response. And then those T cells, can go back then to the local tissue and start killing out the infection. So there's a lot of multi-scale processes going on here. It's a complex system. We want to use mathematical modeling to help understand this system and to find better treatments. And the work here we're presenting today is really oriented towards COVID-19, but we've written in a very general format that we think is going to be very extensible to a broad variety of viral pathogens. So it's not just COVID-19. So also to get this work done, realizing that this is a very multidisciplinary and complex problem, that nobody has all the expertise in-house, we've been going through a collaborative iterative process. So we're going to kind of work through rapid prototyping. We take a design as we think it is today, we build it and test it as much as we can, and then refine it based upon expertise both from within our group and for external feedback when we get it. Use a multidisciplinary team to do this thing, realizing that this problem is big, so we have to break it up into sub-problems. So we have a bunch of sub-teams that each work on their own part of the problem, fed by a combination of domain experts and coders and mathematicians working together. And all of this coming together as open source software with weekly team meetings to make sure that we're really steering in the right direction. And so progress has been fairly rapid. We kind of view this as a three-phase program, where phase one was kind of the active community building phase, where our group kind of kicked things off and said, let's build a few prototypes and use those prototypes to help kind of look for extra expertise that we know we're missing to come in and start becoming and building the community. Then as that community built up, we started training members of the community how to build model components. And then at that point, we could step back a bit and say that we're now in phase two, where we're not doing all the lifting and all the coding. Now we're a little bit more facilitators, and the community and the domain experts and the sub-teams then start coming to the fore and driving the effort forward independently on their own individual components. And then our role is more as systems integrator at that point, that we are coordinating the effort across the sub-teams, making sure things are mutually compatible, making sure that everybody knows about everybody else's progress, and helping to debug and facilitate, the model implementation wherever we can to kind of keep this thing going. And then we hope to arrive at phase three, which is where we are going to hand this whole thing out to the community and say that this is something that we feel is worth disseminating, and put it out as an open source application, put it on the paper, and then move more to community support and training. So the methodology we're using agent-based models, in particular, a framework developed by my lab called PhysicCell, which is an center-based agent-based model. So here's just an example of a heterogeneous tumor being attacked by little T cells that are going in chemotaxing, testing for contact, latching onto a cell, testing its immunogenicity, and then killing it off based upon the immunogenicity, then releasing and performing a random walk to keep finding more cells. So there's just an example of an agent-based model. More generally in this framework, we're going to be using agents for all the lung epithelial cells, and of course, for all the different immune cell types here. And imagine, because it's an agent-based model, it's just an object-oriented programming kind of context. So each cell can have its own ACE2 receptor model and its own trafficking model and state. And each cell can have its own individual viral replication model, which is kind of a nice step of adding some granularity to the model and getting the spatial temporal dynamics of the process. So kind of showing and giving a brief highlight of the iterative progress we've made. We've gone through several versions of our models so far. The first version is a prototype that I actually just developed overnight here on my desktop, starting with a clean slate of code and doing the kind of the bare minimum starter prototype model, where each cell, imagine that you have a kind of a layer of epithelium. Each cell has its own viral replication model. And then you have extracellular diffusion of viral particles. And as a cell gets infected, that is going to be colored more and more yellow here. And the greater the viral load, the greater the probability of cell death. And so we model that as a really basic pharmacodynamic type equation using Hill function. And these black cells are the cells that have died based upon their viral infection. It's a stochastic event. But you'll see that kind of concentrates near this this ground zero of the infection, and then the infection will spread out, where you see a wave first of increasingly infected cells spreading out the region of infection. So it'll be like a viral plaque. And then behind that, then you'll see a wave of black dead cells that start, emanating out from the dead cells in the center of the infection, emanating outward. And then the white bits of tissue are really where the dead cells have decayed away, which would kind of like be exposing the basement membrane. So a really basic version of model. This took us a few hours to code and put online, and actually put it out as a cloud-hosted app on NanoHub. And then we went out to the community and said, we think we might have something, but we really need help. And so we reached out to colleagues, we put notes out on Twitter, and really live tweeted actually as we were developing this model, and got some help and built a coalition and put out our first preprint within a week. After that, our next version said, well, really, virus doesn't just magically get into the cell. It needs to rely upon endocytosis to ACE2 receptor. And so we added an ACE2 receptor trafficking model on top of every cell. The other thing is we listened to community feedback, said, well, it's really cool to be able to model just one virus particle landing and then that spreading infection, but that's not really how it really happens. That the virus particles are landing randomly in the tissue and forming tons and tons of little tiny plaques that then start growing and merging. The other thing we learned is that the virus diffusion coefficient should have been much, much lower. And so we reduced that, again, based upon community feedback, and came up with a second version of the model. So we got much more realistic dynamics now, and we kind of get this idea of how very nonlinear the whole process can be, and this non-trivial geometries of growing and expanding plaques that start growing and degrading the tissue and then merging together. Now, we're missing something kind of big here so far. In particular, there's no immune system. So this is like the worst case of a very extremely immunocompromised patient. So now the next version is really where we started making that transition to community driven. And there's no way we could have done this on our own because we're not immunologists. So we recruited in a lot of mathematicians who are very good at modeling immunologic systems. And a lot of our team members are on this call here today, and then also some wonderful virologists and immunologists. And so we added the first version of immune model where these green cells are macrophages, and they're wandering, kind of randomly patrolling the tissue. And when they find a dead cell that has died, for example, based upon its infection, they will stop there and start phagocytosing that dead material, and then they will activate and secrete a pro-inflammatory factor that's going to recruit in neutrophils and CD8 positive effector T cells that are going to come in and start eating away the tumor. I'm so used to tumor biology, eating away at the infected cells. So here you see some activated macrophages, especially after cell death events. The plaques are still spreading. Let's see here. Now we have some recruited neutrophils that are going in and starting to take up some of the viral particles in the extracellular space and starting to eat dead cells. And then finally, you'll see these red CD8 positive effector cells arriving, and you'll see that they're going to start really attacking the infected cells. Oops. So hoping that I can just pause this, kind of show you the final screen here. You can see that, if you compare the final screen of the model without an immune system, model with an immune system, it has slowed down the spread somewhat. And of course, you can ask all sorts of what-if questions, saying, what if you had more T cells or some resident T cells, for example? Or what if T cells did a better job or worse job at killing? And you get different responses as you would expect. So now we're in version 4, and we're about ready to finalize this, working with the coalition here. In particular, now we said, well, one thing we were absolutely missing is a T cell expansion in the lymph nodes. And so we worked really, really hard with the team, also led by Adrienne Jenner and Trendu after over at IUPUI. Here the idea is that now the cells are not just in the immune, just in the local tissue, but they actually will leave the local simulation and pop up in an ODE scale lymph node model. And then based upon what's going on in the lymph node, you can get a T cell expansion, population expansion, and those T cells will come back in then and start attacking things in the tissue. So that was one of the big changes. We also made other changes in the model to, for example, do a little bit better job of a discrete to continuum conversion, that if you have a field of virus particles interacting with a field of a population of ACE2 receptors on the cell surface, you have to be really careful in that discrete conversion so you don't get portions of a virus particle imported into a cell. You want to have discrete events. So we did a little bit of work on that. The other major things, we started adding the interferon response we just mentioned a little bit ago by adding extra ODE models to each individual epithelial cell and adding a few more diffusing fields in the domain. So here's the full-on integrated model that shows these effects together. So now you have more macrophage polarizations. I apologize, I don't have an extra legend here. But now all these different kinds of immune cells are starting to work together much better because they're able to communicate a little bit more. And the interferon response in particular is doing a good job of slowing down the pace of the infection. I do see a question somewhere in the chat window. I'm trying to figure out how to actually pull that up though. Oh, here's a preprint. Thank you very much. And so really, one thing we were very fascinated with was actually the big difference that interferons make in this process. So let's go back and actually turn off interferon signaling. Well, actually, we can turn off different things in the interferon model. Here we said, let's have the infected cells respond to the interferons that they're making, just slow down the replication, but not have the extra paracrine step. And so they'll secrete interferons, but nobody is passing the message along. Oops. So if I click on this, you kind of see, that we have these infected cells popping up, and the immune cells are attacking them just very nicely, but nothing is really slowing down the propagation of that virus. And so at the end of the day, the tissue is still kind of defeated by the infection here. And one particular thing we find is that there's this gap, right? That interferons are really good for slowing down the course of the infection in the initial affected cells, and the immune cells can catch things that have already been affected enough to be recognizable, but there's kind of a gap in between. In particular, cells can pass on their infection to their neighbors, and they can get infected in that gap between when they themselves start slowing down the replication and when the immune cells start recognizing infected things. So the paracrine signaling turns out to be very, very important. So here now we'll turn on just some moderate paracrine secretion that a cell that's not infected will receive the paracrine signal, the interferon signal, and then secrete its own interferons into the environment to kind of pass the message along as an early warning. And now you can see that the spread of the infection is just drastically reduced, and there's much better control of that infection. And now ramp it up by a factor of 10, and you can see that, we'll skip through a little bit more, but immune cells are going in, they're working together, they're keeping that infection under control. And you can see a lot fewer infected cells kind of on the periphery here. In fact, if we probably had a better T cell expansion here, T cell response, I'd imagine we'd do an even better job of shutting down this particular infection. Other things we've worked with is particularly with Ashley Ford-Forsyth and her team recently at Oklahoma. I think they've moved now though, of adding some tissue fibrosis underneath this that damaged cells when fibroblasts can come in and actually secrete collagens to add some tissue fibrosis. Because one thing we're seeing now is a lot of people who suffer COVID, they may well recover, but they're going to be suffering long-term effects. And I think understanding that fibrosis and other long-term tissue damage will be critical for understanding the longer term of the disease course. So kind of now other ongoing works, like we mentioned, improving the viral binding dynamics and replication models to better account for this discrete to continuum conversion to make sure we have discrete events. We have a much more detailed model of cell pyroptosis led by some of our colleagues over at St. Andrews. And we're starting to add pharmacokinetics and pharmacodynamics for popular antiviral drugs. Next steps is after we get the version 4 preprint out, which we expect in the next week or so, we're going to start right away on version 5. We need to start adding some negative feedback so that there ought to be anti-inflammatory signals to stabilize the response. In particular, we haven't modeled antibodies yet, so that's another thing. And then one key point is, what about if there's nothing in this model right now that penalizes an overactive immune system? But we know that actually there are bystander effects and that the immune cells can damage cells nearby that aren't infected. And that's really one of the worst cases of a runaway effect. So we're going to start working on that next. Version 6, we hope that by that point that we have most of the major effects that we have, we'll call this a final release candidate and start fine-tuning the parameters and preparing for HPC-powered analysis and model exploration and start prototyping 3D versions of the model, which should be fairly straightforward to do. And I just want to point out too that this is a really nice example of sharing expertise across domains. So we have biologists, immunologists, mathematicians who are accustomed to working in different domains, coming together and working on a big problem together and trying to make fast progress. And we've learned to see, some of the ways things that do and don't work for managing big teams. And we think that we could transfer these to, these skills and these lessons to other disease processes. And so it'd be really great to see if we can kind of learn and come up with other rapid responses to significant problems. And really a lot of it just comes from the will to work together and a willingness to put together open source models where you can make fast progress, and having frameworks that are designed to be able to be adapted quickly to new problems. So I want to just thank you all for listening in to our update. And you can try these models yourself. We actually have an online version of this simulator that you can try on NanoHub, and the preprint is out there, and we do expect to be updating again very soon with the version 4 model. And I'm happy to break here for any questions.
Thank you, Paul, for a very intriguing and concise talk. We have time for 1 or 2 questions. Unfortunately, our format doesn't allow us for a lot of time, but I hope that people will contact Paul individually for private discussions, or if we don't have time to get all of your questions answered now. Question or 2?
So I have a comment and a question. This is Reinhardt. It's very impressive work, Paul. And I should say there is, as they say, there's an app for that. There's a subgroup for that on crowdsourcing models. So if you're interested in some of the social and technical and platform issues, we encourage you to join our subgroup. As a question, so Paul, have you? I'm sure you have thought about this. Maybe you can comment a bit on what it takes to calibrate and validate models of this type that are connected together by many different models.
So that's a really great question, and we're in some sense approaching this somewhat in reverse, where we want to get to a point where we have a model that has all the right generic components. We know from our immunologists and from our virologists and other members, pharmacologists in our team, what some of the critical behaviors are. For example, the receptor trafficking, endocytosis, release, the inflammatory modeling, the certain immune components. And so first is just coming to a point where you say that you have a framework that is simple enough to be tractable, but complex enough to get the key components we think are necessary for this complex multiscale system. And once we get to that point where we think all the generic components are working, as we've been going, we've been trying to at least get to order of magnitude correct on most of the parameters, saying, we've been looking at preprints and other data put out by different groups across the world now, which has been quite fortunate, that at least constrain the timescales of different processes. And so, component by component, we're trying to constrain at least the timescales of all the little individual pieces, cell speeds, how quickly they can form adhesions, how long they stick to a cell, how long they interact, all the way up to larger scale things like saying, how quickly do you see interferons at the extracellular level, at the tissue level ramp up? And all of these form constraints on the pieces. We do think that once we have something that's at least in the right ballpark for the general pieces, that's the time we start doing large scale model exploration on the HPC, and then using extra methodologies to try to match more quantitatively to the data as we can get at them. And there are a lot of great techniques to do this, which are now, I think, finally feasible because of high performance computing, particularly approximate Bayesian computation, to help find at least compatible regimes of parameters for the right timescales of behavior. But it really comes down to constraining individual pieces, and then when you put the whole thing together, first to make sure it doesn't fall apart, and then trying to constrain as much as possible. Again, high throughput investigation can also help with that process. But it's not trivial.
I apologize, but I'm afraid we're going to have to move on if we're going to have Bard give his talk.
Okay.
And if there's time after Bard's talk, I'd love to come back and have more questions, because Paul, what you presented brings up all sorts of really interesting things to discuss. And I'm sorry about the format, but I really appreciate that. And I hope that you'll have lots of good follow-on from this. And you're definitely welcome to come back and give another talk when the new version comes out. That would be very great.
Thank you. And perhaps it's a good time to plug your Slack workspace, because that'd be a good place to continue this conversation. We could even make, a channel for each talk if you wanted to, as a Q&A.
That would be great. So if Giuliano, if you want to talk to Paul about that, that would be helpful. Well, okay, and again, I apologize for cutting off the conversation. I don't want Bard to be orphaned at the end of, because we have a hard cutoff at the end of our hour. So we have to. Bard, are you ready to queue up?
Yep. Like just share screen here.
Let me just do a splash screen.
I've done
Hold
it.
on one
Got it.
second.
I'm good. I'm good. Can you see it? Can everybody?
Yes, although we're seeing it in presenter mode rather than
There. How's that?
that looks wonderful. So our next speaker is Bard Ermentrout, who's going to tell us about a very simple model covering the same material. Take it away, Bard.
Yeah, as you would say now, as Monty Python would say, now for something completely different. Okay, so this is sort of a summer project I started with a former PhD student, Erica Motion, and one of James's postdocs, TJ Sego, and two undergraduates, Emmeline Rial and Lauren Gowana, and me. So it's taking a completely different tack. For one thing, it's unfunded. It was sort of a summer fling. I've done this stuff before with not summer. I've done immunology modeling and things like that with Erica Motion in the past, and we sort of started with our. So let me. There we go. All right. So I will skip through all this stuff because you guys all know this already. It's a novel coronavirus, affected 62 million worldwide, killed, well, this is a couple months ago, so it's killed a lot more, attacks primarily the respiratory system, but there's lots of other things that it also attacks, huge variability in the severity. Now this is wrong too. I should have wiped this out. There is a vaccine available. It's just not available to us right now because it's slow on the uptake. And it's very easy to catch, even easier to catch now due to another mutation. So there's lots of modeling efforts ongoing, a huge number of papers on immunology. This talk is mostly going to be about viral host dynamics. There's lots and lots of work on much more detailed models, molecular levels, molecular dynamics models, viral dynamics, Amber Smith and Alan Perlson, cellular and tissue level effects. And I believe this Fader group is the one that Jim just talked about, that Professor Macklin just talked about. And there's also the cellular and tissue level efforts, which is James stuff. I don't think that's connected to this group, right? Is that right?
I'm sorry, which, well.
I was curious.
Judy and Carson, I think, are separate from.
No, Day and Carson are separate. I was wondering if James's modeling was connected to the stuff we just heard today, because it was sort of agent-based.
We've been talking to each other, but they're complementary modeling efforts.
Oh, okay. All right. Sorry. No problem.
No, it's
okay.
Great.
So we're going to do a very simple two-compartment model, starting with a simplified version of our previous influenza model. This is published in JTB in 2015. And we're going to include viral replication in the upper nasal and lower lung respiratory system, some transfer from the lower to the upper, cellular growth and death. There's going to be a small immune subsystem and damage. Model is ODE based, only 9 variables, around 20 parameters. And basically here's sort of a sketch of the model. Can you see my arrow or hand or whatever? Yeah. Okay, so we have the upper respiratory tract, the lower respiratory tract. We have healthy cells which are infected by virus and become infected cells, which then release virions. So this is sort of your standard viral replication model. In addition, the healthy cells die, and this is damage. This is sort of the death of them is damage. That damage induces pro-inflammatory cytokines, which do also collateral damage. I heard that mentioned in the previous talk. These pro-inflammatory things kill the infected cells. They also slow down the viral replication. There's a small anti-inflammatory component, which serves to reduce the pro-inflammatory stuff. And this is one compartment in here. And there's not, so there's just, this is shared between the upper and lower compartments. Okay, so we used, to calibrate the model with all those parameters, we used some data from Munster et al. In Nature 2020. I think most of you guys probably know about this data. Rhesus monkeys were infected in the nasal cavity and the lungs. Virus in the nasal cavity was measured in days 1, 3, 5, 7, 10, 12, 14, and 17, and then lungs in 1, 3, and 5. We took IL-15 as a proxy for the pro-inflammatory variable F. They had very detailed clinical symptom scores, and that was a proxy for the damage we used. And Erica, who's really a master at this, used MATLAB Fit to fit the parameters with minimal constraints. Okay, so here's our baseline calibration to just make sure we were on the right track. Okay, there's the upper respiratory tract, the log of the viral units, lower respiratory tract. In all cases, the monkeys survived. So what we want to do is we want to perturb things so that there's, so monkeys don't survive. Here's the fit of the inflammation and a fit of the damage. Okay, so, and then the other things we didn't have data on, but this is what happens. So in the upper part, there's just a little bit of damage. In the lower part, there's more damage. And you can see that we have the standard infected cells go up and then go down. All right, so with the baseline model parameters, we can manipulate different parts of the model. Since this is cut to 15 minutes, I'm just going to talk a little bit about the inflammaging manipulations, where we change the rate of regeneration of healthy cells and sensitivity to damage. And then what we're going to do is change parameters so that we kill the patient, and we'll see what happens with antiviral and anti-inflammatory things. Okay. So in inflammaging, what we changed here was BHD, that's the regeneration rate of the healthy cells, and GFD, how sensitive the pro-inflammatory response is to damage. Okay, and these are 2 parameter plots, basically. And what you can see here is a log of the growth rate of the repair of healthy cells, and down here is the sensitivity to the immune response. Okay, or sensitivity to damage. All right, and in this case, black is high. So up here, upper respiratory tract survives, lower respiratory tract survives. Virus is wiped out. Virus is wiped out. Here's an example of chronic infection in the lower part, and of course, this is infected cells as well. Okay, here what happens is the virus basically wipes everything out. Okay. So here's some examples of time series. Typical things, lower respiratory tract, when you have inflammation, virus is wiped out, but the inflammation comes on and it remains chronic. Damage remains chronic. Similar things, and here's an example where in the upper, this is the upper respiratory tract. You can think of this as chronic damage to the upper respiratory tract, maybe losing your sense of smell or something like that. The infection remains ongoing. So here's a little picture that I like. I like looking at things geometrically. I kind of learned this idea from my postdoc mentor, John Rinzel. My postdoc mentor almost was Alan Perlson. I just point that out. That was a long time ago. But all right, so I'm going to show you what happens as I change AHF, which is, let me recall that AHF is the effect of pro-inflammatory cytokines on healthy cells. So this is sort of collateral damage. All right. And so with normal collateral damage, what we can see is that the inflammation goes up, or the inflammation stays steady. The lower health goes down, the inflammation goes up, and that stops the virus dead in its tract, and then we return. Okay? If there's too much chronic damage, then what happens is that we go up here and we get stuck in the chronic state, which you can think of as a chronically inflamed state. And finally, if this is really high, if the collateral damage is really high, then basically everything dies out. Okay, so those are sort of the three states. Now, once we've managed to induce enough damage that the virus is what's killing you, we can ask what happens when we put antiviral therapy in. So what we're going to do is reduce the ability of the induced immune system to fight the virus. And then we'll apply antiviral therapy in two different locations, at the viral replication site and at the viral insertion site. And in both cases, timing and strength matter. So here's an example of lower health as a function of time. All right. So here's what happens without, when we put on the antiviral really late. All right. Health goes down, and then just a slow death until we cross a threshold below which no cells can reproduce and we die out. If we turn things on soon enough, then lower health can recover. But if we don't keep it on long enough, then there's still enough residual virus to bring it back down and kill the patient. And similarly, however we leave it on long enough, we can wipe out the virus and return to normal health. Time applied and strength of antiviral, we get this sort of strength duration curve here, and everything in this region is death if we don't make the strength of the antiviral large enough, or if we don't leave it on long enough, we don't survive. Oh no, this is not leaving it on. It's applied for 10 days. This is just the time at which it applies. So we have to get it early enough and strong enough. Okay, last but not least, I want to say a little bit about anti-inflammatory therapy. By increasing the inflammation-induced damage to healthy cells, it's possible to get a chronically inflamed state. There's bistability between health and chronic inflammation in this case, but a great deal of damage is needed to get to the inflamed state. And a strong viral infection can provide that path. So what we explore is timing, duration, and amplitude of anti-inflammatory therapy. Okay, so I'm just going to skip to the geometry here. Since time is running low, well, here's strength. I'll just go right to the geometry because I think this is a really kind of cool picture. And because I like phase planes, it's kind of fun to see this. Okay, so here is lower health along the x-axis and lower viral load in the y-axis. All right, and basically this is a standard. This would be a trajectory. The black trajectory would be one where we come on, all the way on, and we become chronic. We stay in a chronically inflamed state, okay? So that would be too late applying anti-inflammatories, and we stay in this chronically inflamed state, okay? If we put them on too soon, what happens is that the inflammation stops and it doesn't kill the virus. And we can see that the virus is going down, but eventually the virus comes back because there's not enough inflammatory response and we get death by virus. On the other hand, if we put it on at a more reasonable time, then we get returned to full health. And these are just different times at which we turn it on. However, if we put on the anti-inflammatories too late, then boom, we go back to chronic again. Okay, so basically that's summary and conclusions. We found a simple two-compartment model of viral replication and simple immune response can explain recent monkey data. Possible outcomes are back to normal, chronic inflammation, destruction of upper or lower respiratory tract is also possible. There's many attractors and the virus creates a path between them. Mitigation strategies such as antiviral and anti-inflammatory drugs were tested, and there's a good deal of dependence on time, strength, and duration. Still a lot of avenues to explore. And finally, the acknowledgements. It's Eric Emotion is at Carlow University in Pittsburgh. TJ Sego's at Indiana. Lauren Gowana is a Carlow undergrad, and Emmeline Rial is a University of Pittsburgh undergrad. And I want to really thank James Glazier for bringing this problem to my attention. He emailed me, I think, back in April and got me interested. So I'll stop here.
Okay, thank you very much, Bart. That was a very brief summary of really interesting work. It's very impressive to see that undergraduates can have such a leading role in this kind of effort. The work we did also had 2 undergraduates who got it started, and we appreciate that. So there's time for a question or 2 for Bard. Again, we don't have very much time, but certainly time for at least 1 good question. Alan.
Yeah, Bard, like you, I love phase planes, but you have a 9-dimensional model. So how do you reduce it to something that makes sense in 2 dimensions?
Oh, it really is a 9-dimensional system. And this is just sort of, I picked those 2 variables because I think they're very instructive to what's going on. But yeah, there are saddle points in here, which unfortunately have 8-dimensional manifold, so we can't really see what's going on geometrically. We have looked at, for example, a reduced immune system version where we don't even put any virus in there. It's just the immune and normal. And then you can reduce that even further by making a sort of pseudo steady state approximation. And then you can use the intersection of the Lenox lines. But those approximations of the manifolds are really crappy, as you might guess, because there are time scales in here. So this is just to illustrate. Don't think of it as it's not a planar system at all. It's simply just to illustrate these paths and how these things happen.
Do you ever find that, if you actually simulate the exact model and compare it to your phase planes, that the trajectories sort of disappear from that plane and then show up somewhere else so that the representation is not really accurate?
Say it again.
If you actually simulate, the 9-dimensional system and then compare the trajectories that you get in 2 dimensions to what you're plotting, do you ever find that the trajectories sort of leave the phase plane and then some show up later because the action?
No, this was just a projection of the full 9-dimensional.
It was a projection.
So so it is the full 9-dimensional system.
Okay.
And you can simulate it on your phone.
You can.
Okay, is there maybe one more brief question?
One question. What's the main difference between the work you just showed and what Alan showed us about a month and a half ago? Because he was also modeling the upper and lower respiratory system. He had the differential equations there. What's the difference? Your equations are different, or what?
I think we probably used similar viral replication models. I don't know what you guys did for the immune system, Alan. So
yes, we didn't have any inflammation in our system.
Okay.
And the only things we've done is we put in things like an interferon response and sort of a cheat on a T cell response.
So there we go. But
not no inflammation.
Okay, again, I apologize for cutting the discussion short, but I hope that people will follow up. Bard and Paul's contact information is available. These will be recorded. I put in the chat that the prior mini seminars have been recorded and are available, and I encourage people to look at those and see what other people did in this short format as well. Thank you, Bard, again for being willing to present. I want to just outline quickly. Next week, we have Grace Peng from NIBIB. Of course, she's the person who organized IMAG MSM and is sort of the patroness of the working group. And so she's going to be talking about NIBIB interests in this area and also potential overlap between this working group and others and collaborative opportunities. So I think people may find that quite interesting. And then we also have a talk by Macklin of Purdue University and on deep learning based approaches. So going from these mechanistic approaches to AI assisted work. For the 21st, we have a talk on kinetic modeling of an RNA pathogen. And then we have some openings. So please volunteer to speak if you're interested. We don't have to have people specifically from the working group. So if there are people you'd like to hear speak, please contact us, especially send Bruce an email, and we'll do our best to get your favorite speakers on the schedule. With that, I will turn over the rest of the meeting to Reinhard. So Reinhard, I know you want to talk about the subgroups and the meeting tomorrow.
Yes, thank you, James, and thanks very much to both speakers. It's very exciting work that you've presented. It would be great if we had more time to talk about these things in more detail. I want to just briefly in the last few minutes talk about the subgroups. In some sense, a lot of the work, maybe almost all of the work that this working group I think will get done will happen in the subgroups. As you might remember, there's a number of different subgroups on a variety of topics. The first order of business for each of the subgroups really is to produce a white paper that outlines the broad topic of that the subgroup focuses on with an outlook as to what the state of the art is and what needs to still be done, I think, to make this kind of modeling relevant for viral pandemics, maybe COVID, but more likely pandemics that show up in the future. So if you have not signed up for a subgroup, please do so. Different subgroups are in different stages of organization, and there is a spreadsheet somewhere that tells you what the subgroups are and who the co-leads are. So I urge you to consult those. I think maybe somebody, Bruce or James, we can let everybody know where that list is. Now, what we've established is a steering group for this working group, and for starters, the membership of the steering group is simply the collection of co-leads of the different working groups. So it might be, in principle, a relatively large number of people. The way I envision this steering group to function is sort of twofold. In a series of regular meetings, the first one of which is tomorrow morning, in a series of meetings, the steering group or steering committee, whatever you want to call it, really I see as two functions. One is to facilitate communication between subgroups. In what's happening, maybe subgroups will evolve, different groups will merge, some groups will split. So these steering committee meetings could serve that purpose, but in some sense, the more important purpose in my mind is to look at the future of this working group. What is it we want to accomplish? Right. So we have these different working groups, these different subgroups. I'm sorry, that will do whatever it is they do. Different groups may do different things, but then, how do we meld this all together into some really tangible and useful products? They might be articles, they might be position papers, they might be workshops, they might be proposals for RFAs, whatever it is we think will come out of it, or they might be research collaborations. And how do we do this? That's what I would be looking to the steering groups for. What I would like us to do ideally in the last few minutes is to get the input from everybody here in what they think about this, what other things steering group could do, what alternative compositions of this steering committee might be. So please, let's hear your feedback.
Would you like feedback now, or is this just for discussion?
Either now or you're welcome to email me or James. One of the things that we could have done if there was a bit more time is we could have gotten some reports of some of the subgroups. As I said, some have been quite productive already. Others are still in the process of organizing, and so maybe one of the upcoming meetings will have short presentations by the different subgroups to see where it is they are. It's something hopefully we can discuss tomorrow.
So any other business or comments that we should address before we break? I kept us on a tight schedule so we'd have time to talk about organization. So I feel some guilt if I cut off scientific discussion in favor of organizational discussion.
Yeah. So I see Ruchira put a question in the chat about whether there's something written about the organization of this working group. What there is the proposal that James and I put together, which is on the website. You can find it there, that describes, the rationale for the working group and what some of the deliverables will be. So that's a good place to start. Okay, that's really all I wanted to say at this point.
So just to refer to the homepage of the working group. Okay, are there any other business before we break today? We have time for, or you could have maybe a final question for one of our speakers.
Just wish everybody that the new year gets better faster than the old year went bad. So take care of yourselves and start out a good new year.
Our subgroup leads, is there anybody who would like to say anything to the group as a whole? I see we have Yi on board, we have John, we have Gary, we have Jacob. Is there any business that you'd like to address quickly before we break? No?
Nothing specific. I guess we can talk a little bit about overall structure tomorrow as was alluded to.
Okay, well, thank you again to our speakers. Thank you, everybody, for joining. I look forward to seeing everyone as things develop. Please do send us suggestions for speakers, yourselves, your students, people you want to hear, and suggestions for contacts for the working group. In particular, we would really like to have some industrial and pharma representation on the working group. And so if you could reach out to those communities and encourage them to participate, we'd be most grateful. Well, I'd like to say again, thank you for joining us in the new year. I hope it's a good new year for everyone. And I look forward to working with everyone during the coming months. And with that, I will call the meeting to a close. Thank you, everyone.
Thank you.